Today, I'm going to be presenting results from a cooperative study to simulate the effects of highway and urban runoff in southern New England using the Stochastic Empirical Loading and Dilution model, which we of course abbreviate as SELDM. USGS worked with the Federal Highway Administration and the state DOTs of Connecticut, Massachusetts, and Rhode Island to populate SELDM with regional statistics, conduct sensitivity analyses to identify critical variables of concern, and to generate examples that demonstrate how simulation results can be used to inform decision making. In the presentation today, we will provide a brief overview of SELDM, describe the development of that regional SELDM application. We'll also describe the results of sensitivity analyses and take a look at two example analyses of basin loads and of stormwater treatment. This presentation is based on a report that we published a few months back. You can access that online, and we'll be sure to share that link with you again at the end. To determine the effects of highway runoff on receiving water, we need to use simulation methods because monitoring data are limited in both space and time. There are more than 48,000 road stream crossings in southern New England where we might be interested in the effect of highway runoff on receiving water. In contrast, there are 19 highway runoff monitoring sites with sufficient water quality data to characterize statistics for at least one constituent. And those data sets generally range in length from 1 to 4 years. And in this figure, you're seeing a representation of those sites and the duration of monitoring. And you can see there's a gap in the number of locations that we might be interested in highway runoff and in the number of locations where we actually have data available to us. So that's where SELDM and supporting tools enter the picture. SELDM is a stochastic mass balance model that simulates hydrology and water quality for runoff generating events to determine concentrations, flows, and loads. SELDM was developed by the US Geological Survey in cooperation with the Federal Highway Administration to provide information about the effects of highway runoff on receiving waters. And although it's nominally a roadway runoff model, it's demonstrated in this graphic, it's a lumped parameter model, and it has the flexibility to simulate runoff from different kinds of land covers. In SELDM, the upstream and the highway or BMP loads are stochastically simulated from using statistics from published data sets. And those loads are summed to determine the downstream load. That's our mass balance element here. The minimum number of simulated events depends on the climatic characteristics for a particular location. So based on long-term precipitation data in southern New England, the median number of events per year is 52. So in stochastic simulations for southern New England, between 1,400 and 1,900 events were generated, representing a time span of between 27 and 30 years. So from those simulated runoff generating events, we can get risk-based information, meaning we can look at the probability distribution of event characteristics to evaluate exceedance risk. For example, based on the total number of simulated events and the approximate number of events per load accounting year, a 0.558% exceedance risk is the risk that one event in 3 years equals or exceeds a given value. The EPA has specified 3 years as the acceptable risk-based frequency of occurrence for water quality excursions, so we commonly use this metric to compare results among SELDM runs. In this example, we see the simulated population of highway runoff concentrations and highway runoff concentrations with a median performance BMP. So we can ask questions like, what is the risk of exceeding a certain concentration threshold, such as 0.1 milligram per liter? In this case, the highway discharge without a BMP is likely to exceed for about 50% of events, and the BMP discharge will exceed 0.1 milligram per liter in about 35% of events. We can also ask what concentration will be exceeded at a particular exceedance risk, such as that 3-year exceedance risk. And in this example, for highway discharge, that concentration is about 1 milligram per liter, and for BMP discharge, it's about 0.45 milligram per liter. Now, SELDM also provides information about the dilution of highway runoff in downstream flow, and we refer to this as the dilution factor. It's the proportion of the downstream or receiving water stream flow that's from highway runoff. And you'll recall that downstream flow here is the sum of the upstream and the highway or BMP portions. And this is a really useful way for us to approximate a highway's impact on downstream water without having to simulate all water quality constituents of concern. So when a dilution factor is approaching 1, it indicates that we have an increasing proportion of highway runoff in our downstream flow. And we can examine the dilution factors with respect to risk of exceedance, just like we did with the concentrations. And we can ask those same kinds of questions. In this case, the dilution factor associated with the 3-year exceedance risk is about 0.2 without a BMP and 0.1 with a BMP. So with this understanding of how SELDM generates these event simulations, we can then think about using those events to look at total annual loads or yields, because they are assigned to these load accounting years. So we can aggregate them, these thousands, over 1,000 events, into annual loads and yields. So this is an example of what those results look like. And again, we have that x-axis with the percentage of years that equal or exceed a given value with our annual yields on the y-axis. And we can, again, ask some similar questions. But the other advantage to these annual yield simulations is that we can get long-term average values, which can be used in the development of total maximum daily loads, or TMDLs, which is another implementation of SELDM. So now we'll turn our attention to how SELDM was refined with local inputs for Southern New England by working with the Federal Highway Administration and the DOTs in Connecticut, Massachusetts, and Rhode Island. So first, we identified basin properties in Southern New England by identifying all road stream crossings. We delineated those basins and then determined the characteristics of those basins, including the drainage area, length, slope, percent imperviousness, as well as some new characteristics about road lengths and road lengths by road category. We also need to look at the hydrology characteristics, and hydrograph properties, as well as gathering water quality data from highway monitoring stations, databases, and USGS monitoring stations. And these are the kinds of input statistics that we varied for our subsequent sensitivity analyses. Now, in particular, the basin characteristics that we identified in Southern New England, we integrated those into our USGS StreamStats web app. So those characteristics are now available in these 3 states. You can click and delineate a basin of interest and determine the length of roads by various road category. This is really helpful when it comes to allocating our a basin load by the area of highway or non-highway areas. So to characterize conditions and do simulations in Southern New England, we ended up using the highway runoff data from 19 monitoring stations, like I showed before, upstream water quality data from 82 US Geological Survey stream gauges, precipitation data from 45 National Oceanic and Atmospheric Administration precipitation stations, and stream flow data from 385 USGS stream gauges. And with these data, we use these data to refine our SELDM inputs with these more regional values. And these also guided the selection of statistics for the sensitivity analyses. So with the sensitivity analyses, what we wanted to look at is which of these input statistics are most important to specify, such as precipitation, stream flow, or the water quality statistics. So these results are really intended to help refine data collection and analysis methods so that we can improve future simulations. And although we simulated a selection of 21 water quality constituents, we compared dilution factors to evaluate the results of the sensitivity analyses. So recall that a dilution factor is the proportion of downstream flow that is from highway runoff. So this is an appropriate way to approximate the effect on downstream flow. So we can examine the dilution factors with respect to risk of exceedance. And in this figure, we have that This is very similar to the figures that you've seen before, showing the dilution factor with respect to the percentage of events that equal or exceed that given dilution factor. And in this case, this is just an example of what it looked like to accumulate these various sensitivity analyses by varying the input statistic of interest and holding our other inputs constant. So as we repeat these simulations under different input configurations, we ended up with many populations of results. So to examine the dilution factors and compare the variation among these dilution factors, we zeroed in on particular exceedance risks. And again, that 3-year exceedance risk being a common one that we use. So in this figure, the 3-year exceedance risk is marked by that green line, and we can determine a coefficient of variation for the dilution factors at the 3-year exceedance risk among many individual SELDM runs. The coefficient of variation is the standard deviation divided by the average. So this was really a way to get at exactly what it says, the variation in these dilution factors. So when we combine, or when we compare the coefficients of variation at the 3-year exceedance risk across many different sensitivity analyses, many different configurations with input statistics, this is how we can identify variables that have the greatest effect on our simulation results. And as you can see here, there's quite a range in the variation. And what we found is that stream flow, BMP, and water quality selection are the most important variables. And these results suggest that more attention should be given to specifying those inputs for improving our simulation outcomes. Now, advantageously, the data, statistics, and analytical tools to estimate stream flow are much more readily available than for other variables. Now, I should note that the results of the water quality sensitivity analyses were not evaluated with respect to coefficients of variation among dilution factors. To examine the variation in those analyses, we of course were looking at the simulated concentrations and yields. But what we found is that those results also indicate substantial variability beyond what you would see with precipitation or stream flow, or among with random variation in these runs. So unlike stream flow, we need more data to improve the available water quality statistics, and we need research into how to select statistics for unmonitored sites. Because again, we have that substantial gap in the number of sites that we're interested in simulating versus the number of sites we have monitoring data for. So these were some of the important outcomes from our sensitivity analyses that should really guide subsequent monitoring and analysis. At this point, we're going to pivot to those example simulations that I mentioned. So we did example simulations to illustrate a simplified method to estimate the highway and non-highway constituent loads from simulated constituent yields. So we simulated highway and non-highway total nitrogen yields using representative statistics for Southern New England sites. And so that's what you're seeing here, is this range in these long-term, this range in these annual total nitrogen yields that were simulated for highway and for urban sites using the respective input statistics. So what you can see is that the highway and urban runoff kind of average annual yields are relatively similar. But what's important to note is that the highway footprint on the landscape is much smaller. It's a smaller portion of the basin area. So then we carried this through with example basin-wide estimates for 16 tributaries to the Narragansett Bay, just highlighting one of those here. By delineating this basin and stream stats and using our new characteristics, including the length of roads by road category, using those lengths in combination with a representative width of roadway, we can calculate the area of major road impervious area. And with our annual yield that we can assign to that value, we are able to estimate the highway contribution to impervious area stormwater load. So for this nitrogen example, the highway contribution of the impervious area stormwater load in the absence of BMPs was 3.6% of the total stormwater load. And that was also representative of the median among those 16 basins that we simulated. Now, if estimated wastewater treatment, effluent, and on-site wastewater loads are included in that total loading estimate, then the contribution of the highway runoff would actually only be a fraction of a percent of the total load. Our next example is related to the effect of varying our upstream water quality inputs and how that plays out in our on-site treatment efficacy. So for these analyses, a representative southern New England highway site and upstream basin were used with upstream total phosphorus statistics from 62 monitoring sites that represent both developed and minimally developed basins, but do not include any wastewater treatment effluent. So by holding all of the input variables constant except those upstream water quality statistics, we can consider the effects on downstream water quality with and without a BMP. And what we found by examining those 62 simulations is that upstream water quality really impacts the efficacy of on-site stormwater treatment. So that's demonstrated here in this figure with the ratio of the downstream untreated to BMP treated concentrations. And when we compare this ratio, a data point above the green line at 1 means that the BMP treatment is working. It's resulting in lowering the downstream concentrations of total phosphorus. But as these data points are approaching the green line and are a ratio around 1, the BMP treatment is not affected. It is not as effective. Now the x-axis in this case reflects the upstream total phosphorus concentration. So you can see that we approach 1 and have ratios hanging out around that ratio of 1 as the upstream total phosphorus concentration increases. So this is really important when we consider the cost of on-site treatment installation and maintenance with respect to the potential water quality benefits and the importance of specifying upstream water quality statistics. All right, finally, I want to hit a couple of summary points. So recall that SELDM can be used to simulate long-term conditions using statistics calculated from available data. Regional and local statistics were used to select representative conditions. So that's an important part of specifying our input statistics is using all available regional data or local data. Sensitivity analyses indicate that simulation results are most sensitive to the selection of stream flow, water quality, and BMP statistics, but stream flow data and methods to estimate stream flow for unmonitored sites is much more readily available. So attention here is really needed on water quality and BMP. And in terms of the example simulations that we looked at, we saw that long-term annual yields and basin characteristics can be used to estimate stormwater loads from highway and urban impervious area. And finally, in our most recent example, we saw that the efficacy of end-of-pipe treatment is influenced, it's affected by upstream water quality, and that has some important ramifications for prioritizing treatment to improve downstream water quality. All right, I want to make sure to point you towards this report online. There's also an associated model archive data release, which can be a bit intimidating, but it's really valuable because all of these thousands of simulations that we did are cataloged here for subsequent analysis. So please check those out. We'll make sure to put these links in the chat as well. I also want to point you towards our SELDM webpage, where you can find this publication along with many others. You can also reach this USGS SELDM team at seldm@usgs.gov.